So this course, right, if you guys look at it, the whole thing is going to be covering all the way from, say, synthesis onwards. Okay, synthesis would be covered and DFT basics. So we will not be implementing the DFT part of it, but we would be kind of knowing what is that we should know as a PD engineer or as a kind of the synthesis engineer in terms of DFT. Okay, so basically, kind of what is scan chain, what are the different modes, and all of that. So we would actually, learn those basics, and then the whole physical design flow. Okay, where we spend time, most of the time, and then sign off checks and all of that. So complete sign off checks, including STA, physical verification, and IR drop basics, LEC, and low power checks and all of that. So this is how the curriculum was defined. So ideally, if you look at it, so we call it this whole thing as a kind of back end. Now, so the end of this course, right? So you will be able to have a solid knowledge on, say, synthesis, and then you will have a solid knowledge on PD, and you will have a solid knowledge on, say, low power. Okay, and then you will have a solid knowledge on STA, and then you will also have a solid knowledge on physical verification. Okay, and we will also cover LEC part and then IREM. Okay, and your tickle scripting, everything we will have. Okay, now whatever is there in the whole syllabus, so uh, you will have all of that. Now, ideally speaking, this synthesis, okay, PD and STA, PV, low power. So these are all kind of the expertise, you can say, okay, where the tickle scripting, IREM, LEC and all, it is a more of what we do the checks. It is not really you have to do anything, at the time of implementation. It is more of running sign off checks. Okay, so you will get a chance to see everything and learn everything and why important. And now let's say at what stage do you run LEC and what stage do you run IREM, and when you need tickle scripting and how you will have all the things. Okay, so that is how the whole course is defined. Okay. Okay, now, so let's quickly go over what is Async Flow. So let's say you wanted to design a chip. Now, what would be your first step? So the first step is to get your specification. Okay. So now, what is the meaning of specification? So if you look at, right, say when you say specification, it is basically your power. Okay, your performance. Okay. Say for example, performance is nothing but frequency. Power is nothing but you guys know how much power it requires, and then area. Okay, and then what are all the IPs that you really need? What are all the IPs that you need? What are all the IPs that you need? Say for example, when I say IPs, okay, say you have ADC, okay, you have DAC, and you have ARM CPU, okay, ARM GPU, and then your PCIe interface, okay, and then your DDR interface, okay. So these are all some of the IPs, and then you may have memory bank and all of that. And then the next thing is a technology that you wanted to implement this chip. Say for example, your customer may give or may not give. So tech node, what tech node? Say for example, you have got 7 nanometer, you have got 5 nanometer and all of that. Okay, and then your package type. and then you need to have your package type. Is it flip chip or it is the wire bond and all of that? And so these are all kind of say specifications, and then or requirements. And once you get this from the customer, okay, and then now you need to decide what is the best way to put this across, okay, or all the kind of how do you expect these IPs uh, are going to interact among them, and then how are you going to achieve say ARM CPU, say frequency of say 2.4 gig. Okay, so now how are you going to achieve this 2.4 gig and all of that? So it is basically they would decide what kind of architecture they wanted to choose, or what kind of so how they wanted to arrange the IPs, so which would bring down the internal throughput time and all of that. So the next step would be internally your management, your senior folks would get into kind of the architecture, micro architecture planning, and in a such a way that your power can be minimized and area can be minimized, and all of that. Okay, and then once you are done with that, the next thing would be kind of say RTL design. Now remember, when we take any design, when we take any design, we will have multiple IPs. Okay, so you may have the IPs kind of like this. Say for example, you any chip that you take, you will have kind of say CPU subsystem, say quad core, L1 cache inside the core, and L2 cache, and then say graphics core, then your DSP core and applications, custom applications, and then say modem. Say you have a DDR5 and USB 5, PCIe, Ethernet, and then your Bluetooth, wireless LAN, and high speed interface. And these are all kind of the low speed interface and all of that. So these are all the kind of components that you will see in, typically you will see in each and every design. Now, so if you look at right, a typical IC will have say kind of memory array, a PLL, and your USB interface, and then your temperature sensor, your process monitors, and many other sensors. Okay, and then your analog to digital converter and peripheral control interface, modem, your analog and mixed signal IPs. So your GPU, CPU, and then GPU or your DDR, and then you will have your IO pads and all of that, and then you. So once you have all that modules identified, right now there will be each team will work on separate things. So as I said, right, so there will be a CPU team separately, and a GPU team separately, and a PCIe team separately, and DDR team separate. Okay, so the teams who are specialized in CPU, they will start coding in RTL. They'll start the RTL coding activities. Okay, and they will try to reuse, sometimes reuse the previous version of the code and etc. And once you start that RTL design activity, right, now this is, so they'll give you the spec, and then you are actually coding that. Now how, who's going to verify that whatever that someone is writing the code here is basically you know meeting the specification or requirements. Now that is the time where your RTL verification team comes into picture, and they actually go and verify whatever the RTL that is written by these guys, I mean the RTL design team, against your spec. Okay, against your spec. So they come up with their own test vectors and test benches, and then they try to uh, ensure we are actually in line with the specifications. Now once this is done, now what is the meaning of RTL? So when I say RTL, right, it is like each and every, the whole code is going to be kind of say behavioral model. So it is kind of Verilog coding or system Verilog. Okay, so it is kind of going to be behave, any other programming language. It's just that they would be kind of, we call it HDL languages, but they all going to be kind of, a programming language. Now the next thing is going to be converting this HDL into RTL synthesis. So you would actually convert the code written by this guys into say in the form of gates. Say this is the kind of say gate level connections. Okay. Now say converting a kind of a simple program, HDL program into kind of an gate level netlist. So that is what we do in RTL synthesis. Now, when you do RTL synthesis, again, remember you have to make sure your design meets certain targets. So, what are all such targets? Say your frequency is one of the targets. So 2.4 is one of the targets. For example, for if it is a CPU, if it is some other design, they will have their own frequency definitions. So they will take care of all of that. And then say your power. So they will look at what kind of libraries they wanted to use, what kind of pros PVT corners that they wanted to use. Okay. And this is where they actually target a technology. This is the time where they actually target the technology. So till here, so if you look at right, so till here, literally there is no technology coming into picture. It is a kind of say generic code. It's a kind of generic code. That code can be implemented in say 7 nanometer, okay, or 5 nanometer, or even 3 nanometer, and etc. Okay, so 3 nanometer and etc. Now, RTL synthesis is the place where the first time you are getting into the technology. So you might ask me, Kumar, so then some people might reuse the RTL from one generation to another generation chips and etc. Yes, they would reuse, but the major benefit of your PPA. So, for example, power, performance, and area. So this I always call it as a PPA. Okay, PPA. Now this would be targeted, the target, the PPA target starting from here. So that doesn't mean that it's actually starting from here, even the architecture onwards. So your PPA is basically started all the way from the architecture. Once you gather, and they, as I told you, right, so they have to know what architecture that would bring down your performance, bring down your power, increase your performance and area. But the real numbers you would be able to get to know only here, RTL synthesis. Okay, so this is the first place in the flow, or first stage in the flow, where you actually bring in your libraries targeting your 5 nanometer or 7 nanometer and etc. Okay, and then so each and every chip that we design, okay, we will have to test them. Okay, you cannot deliver them as it is. Now we add the scan, the testability logics and etc. So that is actually taken care by the DFT team. Okay, now there they would design, or say what is the meaning of compression and what kind of compression architecture and decompression and all of that, and then scan chain informations and how many flops per chain, all of that. So the DFT team will decide. Now remember one thing, they see end of the day, right? Anything that you are doing from synthesis, all are done through a scripts. Okay, all are done through scripts. So you just need a kind of a script which will help, which will take the design and then do all the steps and write out all the outputs. Okay, so the same way the DFT team will give you a script, so you can plug in and continue, or there are companies who, after synthesis, you give it to DFT team, they do their work, and they give it to physical design team. So I have seen both the models. So end of the day, you either you may be responsible for adding DFT with the help of DFT team. They will provide you the scripts, or you would actually deliver your design to DFT team, and you just give them a week time and let them come back and then give you the details, the inputs. Now we get into the physical design. Okay. Now when I say this physical design, now see, this is kind of your gate level netlist. Now this gate level netlist is, right now, it is no area is kind of targeted for the physical die area. Now what we would do here is, physical design is the time where we would actually go and decide something called die size. Okay, say this is your IC size, this is your die size. So we call it as a die size estimation. Okay, so we start doing die size estimation and optimize it and all of that. Okay, now this is going to be your full chip. Okay, this is going to be your full chip. Now we will also talk about why it is important for you to learn the die size estimation, so that you know how you are going to contribute your chip, or say the overall revenue. Okay, so die size estimation and optimizing the design, uh, for a perfect area, I would say perfectness. There's nothing called perfect area. So to have a lesser area and etc. And then we will do complete place and route, and then STA and all of that, and run all the sign up checks. So and then finally, if everything is clean, then we go for tape out. Okay. So now this is kind of the ASIC flow that the industry is following. Okay. Now, so I will explain. There is a slide that I have. Next slide. I would actually, explain physical design little in depth, so that like you guys know what you are going to learn. And then, say you are done with the tape out. Now, what is the next thing? So now you are done with your tape out. Now, is that done? Okay. Now your foundry goes and takes your, the design and the manufacture, and then what we do is we bring up, say, chip in house. So we bring the chip back. So after 5 months, you bring the chip back to your office. The foundry will, whatever the tape out you have done, now they would actually now give you the chip back. Now you actually have a tester. So you test each and every chip. Okay, so there are different testing. Okay, so that would be carried out by the DFT team. And then finally, once the chip is working fine, and then all the good chips would be now given to silicon validation team. Okay, silicon validation team. Now the silicon validation team would actually apply all your real functions. Okay, say for example, if it is a Android, say if it is a mobile chip, they would actually load the OS and they check your Bluetooth is working, if your Wi-Fi is working, your calls are going properly, is there any call drop, okay, is that HD calls or 5G calls, and then Wi-Fi calls, and then your, how is your power and how is your battery, and so each and everything. So they kind of, try to see your whole thing. So it's with the board and etc. So the silicon validation team will try to check if this chip is basically working as per the spec. Now, remember the whole thing, right? So when I say this whole thing, right? Say now finally, so say for example, customer, okay? Say customer, say OnePlus. Now he's going to launch a new phone, so he need 5 lakh unit. So he's planning for 5 lakh unit. Now, so when you tape out this, so we just, how many chips that we order first? We just order some thousand chips only first time. We will not order all the 5 lakh in the first time itself. So we'll just order 5 lakh chips. Sorry, only 1,000 chips, and then we test everything. If we confirm that if everything is working fine or not, and then let's say there are some bugs. Okay, now what we do is this whole first thing, right? It is called version called A0. Okay, now the next thing is, so if there are bugs, you know what we do? We try to go and fix those bugs and do one more round of fabrication, one more round of tape out. We will not follow all this. We just take the DB from this, whatever that we have delivered. So we just try to uh, fix those bugs that are seen, and then we try to again tape out, A1 tape out. Okay, and again, so we bring chip in house after the tape out. They will give you again first 1,000 only we again take. Now again we test. Now say all bugs are clean. Now we are good, all good. Now you know what? Once we verify and we also provide some of this 1,000, right? We also provide to one plus some 100 chips or something. They go and test it, and once the customer one plus says, okay, we are ready for production. So once all the testing is done with based on this basic small number of chips, or prototyping and then validation, or all that, then we go for a final production. Once the customer says, okay, so I'm good, now let's go for one plus the final production. Now this is the time where we go for all the 5 lakh chips manufacturing. Now, so once you give order, it takes again say 3 months to get the chip, and then we deliver the chip back to OnePlus, and they take 1 to 2 months, okay, for assembly, for the chip, the mobile assembly, and then they announce the sale. So this is how it actually happens in the whole industry, the whole application bring up, ideally speaking. Okay. So I would like to pause here for a minute to ask questions, if any, or any doubts.
Sometimes B0 uh, trip out also comes into picture. So, what is that scenario?
Okay. So now B0, see, it is kind of A0 and A1, right? Now, say A0 is targeted in, say, for example, the A0, A1, and all of this. So these are all kind of targeted in 7 nanometer. Okay. Now, so there could be some competition. Say, for example, OnePlus now, I have ideally wanted to have more features and better resolutions and all of that. So, you know what they do? So they target now B0, the same functionality, the whole thing. Now it's just that they target in 5 nanometer, for example. Okay. So it is basically A0, it is same functionality, the chip size and the internal functionality and all of that. So B0 would be similar. Either they take advantage of less area, or they add more, they try to see, what actually happens is, say if this is your mobile motherboard, now you will have your main chip like this. Okay. Now, say A0 size is, say, this. Now, when you go from 7 nanometer to 5 nanometer, one technology node, right? And you scale down, I'll explain you guys what is the meaning of scaling down, and one technology to another and everything, in the upcoming classes. Just today, understand that. So it is going to be smaller in size. So now, when you manufacture the same chip, basically you implement all the things and everything. Now, say B0. So B0 would be kind of, say, this is going to be the size of B0. All the exactly assuming you have the same module, same IPs and all of that. So it is going to be exactly the same. Now, there are two options here. Either you use the same smaller size and then try to bring down your size or make it sleek and etc. That is one option. Or in your A0, so you have given say 8 CPU. Okay. Now in B0, you might want to add 10 CPU. Take, provide more performance, so that your area remains same. So this area remains same, but just that you are getting more and more features. Okay, so now what does this mean? Why are we doing this? So that your socket compatible. So there is a word called socket compatible. Socket compatible, or people even called it board compatible, or board or package compatible. Okay, so socket. So now you just have to take off this chip, put this B0 chip, and continue. So you don't need to redesign. Say, for example, OnePlus, right? So if you are a OnePlus person, you don't need to redesign your motherboard. Motherboard is already designed, so you can reuse. So just that you are just removing the old chip, which is kind of done in 7 nanometer, say kind of heating or kind of more power consumption and etc. Now B0, that is something kind of optimized. Now you're just replacing the chip and continuing. So there are revisions. So if you look at, right, in industry, A0 version is going to be really, really tough. So when you get a chance to work on A0, you would see lot of challenges, and people go through lot of experiments to meet the targets and etc. So A1 is going to be relatively easier. So now remember, A0 to A1, there would be only minimal change. There would be only minimal change. Okay. Now B0, there could be a major change. That is a basic thing. So when you say B0, there is something that we look at, a major change. So when I say major change, so there are certain layers in VLSI, we call it. So we have something called base layers, and then metal layers and all of that. See, A1 is always, we try to limit only to metal layers change. We don't touch base layers. Okay. We don't touch base layers, but whereas B0 meaning complete layers change. So probably you may not understand this at this moment, but you will gradually you will get to know each and everything. So if you guys look at, right, this versions A0, A1, B0, B1 and all of that, you will hear more in server chips. Okay, so Intel server, AMD server, or processors. And then even in Qualcomm and MediaTek, you will hear a lot of such things, because they keep, there are a lot of customers who would keep buying these chips, and they request, okay, this functionality I want, or that functionality I want, and so they keep adding those functionalities and etc. So you would see there are a lot of revision chips going on in the Intel, and then AMD, and then Qualcomm and etc. MediaTek and Broadcom and all of that. So A0 chips are the one which is kind of more and more challenging. Adna, I hope I have answered your question.
Yes, thanks.
Okay. All right. Now let's. Any other questions? Okay. So let's get into the next slide, where we will just talk about the physical design flow in there. So, so the physical design flow. So this is what we are going to learn in depth. Okay. So now, if you look at, right, since we are not the creator, so when you say physical design, right, you are not the creator. So don't think that yourself, okay, I wanted to be into design and things like that. No, see, design team definitely they need a lot of programming skills. Okay, so this team needs a different skill. Okay, and this team needs a different skill. So definitely this team, the whole front end part requires a lot of programming skills. Okay, and anyone who's kind of hates scripting, they prefer always coming to the back end. uh, okay, so first of all, I hated programming myself. Basically I hated scripting, basically programming when I was in college. So that is the reason I chose to VLSI, thinking, okay, there will not, it's a core domain and etc. And then after coming into this, I have been doing, design plus CAD role where I automate lot of things. Now the reason why I'm saying is this CAD and automation, right? You actually work with a lot of scripts. So when you are in a junior level, say below 3 years and etc., you try to learn what is there inside the scripts and everything. So I'll show you what is meaning scripts and everything. And then at some point of time, you start writing your own code. Okay, so that is how you become a strong resources in the team, or say I would say critical resource in the team. Okay, so do I really need to know scripting to be a PD engineer? The answer is definitely no. You don't need. But if you ask me, can I go and learn? Definitely yes. You should learn it. The reason behind is you would actually make lot of contributions, and then your job is more secured when you know little bit of scripting. Okay, compared to a person who's kind of non-scripting. And moreover, when you go out, so remember, the scripting person salary is always little higher than the non-scripting person. Okay, the market value is always higher for the person who knows scripting, and a person who's kind of not sure of or kind of staying away from the scripting, right? People will try to there is no rejection, but your salary could be kind of, people might try to say, okay, so this is the skill that you possess, so this is what, based on the skill that whatever that you possess, you would be offered, this is the kind of limit that I have, something like that we used to say that. Okay, so definitely, if you ask me, we would actually focus on little on the programming as well. And my suggestion is that you start looking at basically tickle scripting, so you don't need to worry about the C programming and C++ and all. So TCL is the language that I am going to use. To be honest, this whole tickle scripting is really really easy. Okay, it's just that you should know how to learn and what is the meaning of algorithm and etc. So we do have this in the curriculum, and I'll try to help you out as well, but it will not be covered in the expert level. Whatever the basic level that is needed, we will cover in this course. Okay. Okay, so physical design flow. Now, see inputs. Okay, so your designs, your libraries, your area, and all of that. So, get all the inputs first from the other team. Okay, and then the first step is to check if you have got all the quality inputs. Okay, so remember, you cannot make a great dish with the base, uh, if you are using a kind of spoiled vegetables. Okay, so you should ensure that you have got all the kind of the quality inputs to prepare, say, a good dish. So that is the same thing applies here as well. So if your inputs are not good quality, you will not be able to close the design. Remember, so you will not be able to close your design with the quality that your manager is expecting. So your manager, what he would say is, whatever inputs that you have received, is it all good quality? So there is something called sanity check that we do. Okay, so on all the inputs, so we will try to learn that as well. Okay, and then floor plan. So this is the time where we look at die size estimation, and then play your shape and all of that. Okay, now let me just show you how a full chip would look like. Okay, now if you look at, say, this is your full chip. Okay, so this is your full chip. Now if you guys remember one thing, so how our ICs are getting manufactured. So the first thing is, so now if you guys look at, right, so this whole thing, it is called the silicon ingot. Okay, so the whole thing is that, say, it's kind of, you will have, the first thing is from the sand they prepare a silicon ingot kind of thing, this kind of, the silicon cone, and then this would be chopped into a finer pieces. Now it is like kind of exactly like a puppet. Now this is something we call it, it is kind of going to be like this in the round shape. Now on this round shape you would actually manufacture your chip. Okay, so you would actually manufacture your chip. Now how many full chip you can manufacture in this one wafer? So it is something we call it as a silicon ingot. Okay, now this is something we call it as a wafer. Now this is something we call it as a die. Okay, now, so this wafer is having, it's a kind of different sizes. Okay, so now if you are going for a volume production, you would probably use a bigger wafer and etc. So now, assuming this wafer, say currently your chip is, say, kind of 10 mm by, say, 12 mm size. Okay, now this size you would be able to manufacture, say, kind of 1,000 chips in one wafer, 1,000 chips per wafer. Okay, now if you can optimize this area, okay, so this 10 mm by 12 mm, right? Now if you can bring down this 10 mm by 12 mm to, see, for example, the way, better optimizations and the better floor plan and area estimation and all of that, say now 9 mm by, say, 11 mm. Okay, you have done some, extraordinary area planning and what is needed, what is not needed, and all of that. And then if you are able to now bring down this size, now the same wafer, now probably you will have, say, I'm just giving you rough numbers, say 1,200 chips per wafer. Okay, 1,200 chips per wafer. Now the wafer cost, the each of the die cost would come down when your area is lesser. Okay, so people always prefer packing more and more, chip in a wafer, so that their manufacturing cost. Now remember, say when you're building a home, say there is a plot cost, so you buy a plot and then you go and, build your home, so that is manufacturing cost. So now your manufacturing cost is, say, 5,000 rupees, or say $5,000 per wafer. Okay, now in this case, it is going to be $5 per wafer, sorry, per die. Okay, so $5 per die in this case. Okay, now whereas here the same 5,000, it is going to be around approximately less than $4. Okay, less than $4. So your company would make more profit. So that is the reason we always try to, prefer to reduce the area. Now you should actually know what are the different methods that you can use. How can you assign IPs, or plan your logic placement or IP placement and pump placements and all of that. So the company would actually, try to take advantage of having a reduced area, the IC area, and they eventually spend lesser, and the company will have money, and they will be able to, say, kind of, show growth. Okay, so ingot to wafer, wafer to die, and then this die is nothing but your full chip. Okay, so now that die is nothing but your this whole full chip. So whatever that you see here, right? So this whole thing is your die. Okay, now this die again consists of, there are something called IO pads. Okay, and then there are IPs. Okay, and then your logics. So this is one block, say this is another block, and say this is another block. Now if you plan it wisely, okay, so probably you, if you can bring this, say this size now into, say kind of, say this size, say put all your effort and bring it, say this much, you just try to save this area. Okay, you still make more money or save more money than what you are actually doing. So that is the reason. Say now, do I really need to place all the IPs here? Okay, is there any other better place which would make me bring down the size and etc. So the whole thing is happening, or the whole analysis happens at the time of your floor plan. Okay, so floor plan is the first step where it is very very critical in terms of your area estimation and then area optimization and etc. Okay, and you need to hook up the power and all of that. You need to hook up the power and all of that. Okay, and the next step is your placement. So we will have, there are lakhs and lakhs of cells, the standard cells. Okay, so don't think that okay you would be able to manually place them. So there is something called a standard cells placement. So we actually let the tool do the whole standard cell placement, and then there are certain things that we look at. When I say things, meaning your timing, your congestion, and utilization, and all of that, you would actually have to look at it, and all that we will look at it. And then again, you may wanted to do a timing optimization and all of that. And then once you are done with all this, and remember, if you are able to get your floor plan and placement, if this and this, the whole things, floor plan, placement, and your timing, your 70% of your design is closed. Okay, so if you are able to bring, get your floor plan and placement, and then your timing, congestion, and utilizations, and VT percentage, and all of that, your 70% of your design is completed. Okay, now the next step is to build your clock tree. So there is certain, now each and every stage, right? So you will have a goals. So floor plan, what is the goal here? Die size calculation and area optimizations, and then IP placement, and then PG hookup and all of that, making sure your base DRC is clean and all of that. Now coming to this placement, all the standard cells has to be placed in a legal locations, and then optimizing the timing, setup and hold. You guys know that, and you might have heard of, I'm not saying you might have learned in your textbooks that setup time and hold time and all of that. So you would actually have to perform setup check here. Hold we will not be doing before CTS, and we will not discuss why we don't do hold before CTS and all of that. So CTS also will have us different goals. Say mainly we have a something called insertion delay, and you will also have something called a skew. Okay, so these two are the main things in the CTS, and then there is again little more in depth. So when we get into CTS, we will discuss in detail. So CTS, you build your clock tree and then verify or check if it is everything is kind of meeting, and then again timing analysis and optimization. So here you look at your DRVs, and then your setup, and then your hold and etc. Okay, and then perform the routing. Okay, and then after routing, there is again we have a certain goals: 0, opens and shorts, okay, and then 0 DRC. So this is the goal of routing, okay. So are we able to achieve that? Now if we are able to achieve, your design is almost 95% closed, okay. So remember, you have, if you don't take care of certain things in each and every stage, then you will have hell amount of problem in the later stage. So physical design is not okay, run the flow and go and just check the results. No, not that. So you need to make sure floor plan, yes, you have checked all that then and there. Okay, then you go here. So this whole thing that we call it as a correct by construction. So you cannot, you have to keep correcting your all your things and then make sure then you move forward. Okay. Now, so once your routing is done, and then you can actually do the sign off checks. Now what are the different sign off checks, what are the criteria that you can move forward, and remember one thing in our class. So you may have some issues in the placement, for example, you may have some issues, but how can you make your decision to go back and fix it or move forward? So that level of intelligence you would actually look at it, okay. So each and everything, every stage we will have a QA checks, and then if those QA checks are failing, what should be your decision, okay. And then you can, make your decisions to go forward or fix it and move forward and etc. Now sign off checks, are there any waivers? Okay, so we would look at, each and everything in the, throughout the, flow, and make your decisions and then look at warnings at each and every stage and all of that. And then finally when we are ready, then we would actually, if, say, remember, you might be just working on one of the block. Say for example, you might be just working on this particular block, you may be a owner of this particular block, okay. Now that doesn't mean that once you finish your block, we won't be able to tape out, okay. Now all this guy, so this guy, this guy, this guy, this guy, and everyone has to be kind of, everyone has to be closing their designs. So it is a teamwork. So it is not individual work here. So everyone has to close their designs before you go for tape out. Okay. So now you all the blocks closed. Now we integrate, take your block and run all the sign off checks at full chip level. Okay. And then there could be some feedbacks coming from your full chip to blocks and all of that. And then we would actually, go for a tape out once your full chip is clean, and then your tape out date is, kind of shuttle, or your own, you know schedule is confirmed, then we would actually target such particular date, okay. So any question here in the speedy flow before we move on to seeing the tools and the labs?
So one question, when it comes to the area consideration, suppose we're trying to
Hey,
reduce some
your
area,
voice is kind of,
so there might be a chances of increasing
hey, there is a voice kind, your
breaking up.
voice is kind of going off. Can you probably, keep your mic or probably move to a place where you will
Now
have a
can you
good
hear me clear?
internet connectivity? Yeah, go ahead, Dinesh.
Now we're clear, right?
Yeah, yeah, go ahead.
So when it comes to the point of area consideration, suppose we are trying to reduce some level, so there will be a extension of power consumption, right? So, do we have any such kind of methods to organize that power and area?
Yeah, we will have everything. We will discuss all of that. So throughout the flow, right? So you have, we kind of have different optimization techniques that we might use to optimize the whole thing and all of that. Say you wanted to target your performance, say CPU, right? Say in this case, say you have a, say CPU. Okay, say this CPU, this would run at, so the whole CPU system would run at say 2 gig and above frequency. So this eventually need to focus more on the performance. Okay, now graphics might be around 800 megahertz, and then the core, signal processing core, it might be around 650, and your custom cores maybe 1 gig, and your modem and all somewhere around 600, and then your DDR, USB, and all of that. So each of the design will have their own different frequencies. Now, if you guys try to look at, right, so P is equal to C V squared F. So these all things we would be covering again, basics. So higher the frequency, you will consume more power. So you would actually try to optimize your design in a such a way that you will target your PPA. So we have something called multi-VT libraries. Okay, we have something called multi-VT libraries. Say for example, you have a HVT library, and you have a RVT, and you have LVT, and then you have ULVT, and then on top of all this, you also have something called multi-channel library. Multi-channel library. So you have a short channel, and then you have a long channel. So you try to choose the cells that is going to help you to meet your PPA targets. Okay, so to answer your question, so the whole PNR flow, right? So you would actually try to target what is the best practice or best optimization methods that would actually yield, or probably that will help you to meet your PPA targets and all of that. Okay, say here you can say area recovery. So after your placement, there is something called area recovery that you can actually do, and that would eventually help your timing non-critical paths, reducing the cell areas, and eventually that will lead to your lesser area and lesser power and etc. So again, CTS, you might be interested in choosing the right cell and right transition and then right skew that would eventually bring down your clock tree power. So there are a lot of such things are there, so that eventually you will actually kind of we will cover all of that. Dinesh, did I answer your question?
Yeah, got it. Thank you.
Any other questions?
Hi, sir.
Yeah.
So I have a very, it may be a little early that I'm asking this question, but as you said that different blocks owners run, different block level designs, and then at the end you integrate it.
Exactly.
So, like ADC or DAC, this there are different engineers, those who do it. I mean, engineers. I mean, say a different team. Like there's a
Yeah,
ADC team.
exactly. So that's exactly what even I was saying. Say for example, this CPU would be done by a different team. Eventually, the CPU team is going to be much more experts than any other team. So,
Hmm.
say graphics guys will have a different skills, and these guys will have different skills. Now, for example, DDR, there are a lot of custom requirements in this. So, this CPU engineers cannot work on this, and the DDR engineers cannot work on that. So, you go ahead. Yeah, there would be a different teams, even obviously.
Yeah. So basically, my question that I wanted to ask. So when you say the blocks is getting ready, what as a PD designer do I do until then? I mean, I have done, let's say, with the floor planning, and the ADC comes around, which is not the expected floor plan that I kept in, or something like that.
No, no. Okay. So what you are asking is if there is a change in the area of your IPs. Is that right?
Hmm.
No, see,
Yeah.
it
So
is. Go it, go it.
sorry again. So
No
let's say
worries.
you are the main person who integrate all these designs,
Correct.
and I am working in the EDC in the PD side, and
Okay.
somebody else, let's say Dinesh, is working on the CPU.
Okay.
And so because you are integrating it, so whatever the changes that I do in the design, that also affects
I will
you,
have
right?
to take every changes. So, say for example,
Okay.
now, just to give you, for example, okay, let me give you. Let me just go back to my this full chip. Now, say for example, now all this full chip. I'm say assume I'm the owner of this full chip. Okay.
Mm-hmm.
Okay. So Kumar is the owner of full chip. Now say this you are owning. So Devesh. Okay. Now say this is Dinesh. Say this is Abhi. Okay. So now, so these are all say Pujita. Say this is Som. Okay. Say this is Bala. So now I would say for example, now guys, all your blocks needs to deliver. Say today's date is July 1st. So by 10th July,
Mm-hmm.
I need your base clean DB, base LVS clean DB. Okay. So now, for example, various reasons. So Divesh is kind of, he has kind of more issues in this blog. He's kind of getting delayed. You know what I would do? I will just leave your blog and I would check, I would take the blogs from all other people because they might have done. Okay.
Mm-hmm.
Now I would run my full chip activities, full chip sign off checks, and wanted to, check if there are, if everything is clean from the full chip level, excluding your block.
Okay.
Okay. Now, what I would that would ensure is the moment your block is available, I would have to redo everything. But just that I would have finished all other blocks. See, remember when you are a company, say for example, you are a company of Qualcomm, your management would be always worried whether we will hit the tape out date or not. So anything that is making gaining the confidence. Now, say for example, by July 10th July, all other blocks released. Now, say
Mm.
30th July, I'm taping out.
Okay.
Now, this month end is my tape out. Now, what I would do is I would actually collect all the blocks and 10th July, I just start iterating. And your block, you're saying you would be able to give only on 15th July. Various reasons. I'm not getting into too much things. Maybe your IP came late, or you have some issues that is kind of went for re-spin and all of that. You're doing whole read PD and all of that. So
Mhm.
your expected date is only 15th July. Now what I would do is 10th July onwards, I would look at all the other blocks, collecting them and integrating and running all the sign off checks, and I would try to give all the kind of feedbacks by 15th July. Okay. Say, ideally speaking, I might give them the feedback by 12th July. Now they fix and get back by 13th. Now again by 15th, I will have one more round of feedback. So multiple rounds of feedback that goes in. Now the moment you come in, I will take. So once your block is closed internally, you might have closed at block level. Now interface, say for example, all the edges. Is there any route coming closer? Is that is causing any DRCs? Whether is there any power hookup that is kind of causing you the trouble and all of
Mhm.
that. So ideally I have to verify everything. Now this is the time where your full chip PV, okay, full chip STA, and then full chip IR, and then full chip flat LEC, and all of that we do. Okay. So we need at least 20 days to get each of them run, provide feedback, fix them and get back. So though you might have closed your block, there will be feedbacks keep coming in from the top level, and then you will have to keep rolling them in. So this is how people actually work. So till the time you have a tape out, you tape out the chip, nobody is going to be just free. Now you know what I would do. Now what is the guarantee that you will give me 15th database? I won't trust you. I'm say if I'm your full chip manager, I will I'll trust you, but I will have. Now say Abhinay have finished his runs. Now you know what I would ask Abhinay, can you run this in parallel? Can you take this design and can you run one more round along, as Devesh in parallel? Now, say some issue that you have, but Abhinay is run, Abhinay has different skills. Now Abhinay have closed the design, or say he reached the design. So now I would not take your design. I would take Abhinay's design and I would go and do the takeout. So this is how each and every managers will mitigate the issues. Okay, see,
Okay.
end of the day, your tape out date is fixed. If you miss the tape out, there there you need to, the manager, the project manager, or the person will have to answer hell amount of people. Okay, and don't think that they'll just only come on only 30th. They start tracking you from 15th or July 1st onwards. There will be weekly updates, and then what is a critical issue, are we on track, how many blocks are uncritical. So what kind of help you need. You need more people. Okay, ask for more people. You need more resources, more licenses. So there are so many things that goes in, ideally speaking. Okay, so this is exactly what happens in industry. And people, I know you are from, you are working, and you might have heard about this all, but the others, uh, these are all the things that nobody will even tell you outside. So how the integration happens, and the final stages of the tape out, how it is going to be. So this whatever that I was talking since 10 minutes, right, in the last 10 minutes, this is exactly what happens in the industry.
Thank you, sir.
Any other questions? Okay, and I'm basically an Encore expert, and so I have a habit of reading all these documents. So the whole course is going to be more on the PPA based targets. Okay, so I collect all this kind of documents, which is kind of say Snug and CDN Live and all of that, and you would actually get the knowledge whatever that is over here they present. So it's kind of a conference where people will come and present what they have done and all of that. So you would actually learn all these techniques. So end of the course, these papers would be shared, and exactly what we are actually talking, say kind of say 7 nanometer FinFET, what are the different challenges, DRCs, and then pin accessibility and lot of things. Okay, so what are the best thing that they have followed. Okay, so how your logics, what and all you need to check. So all these papers would be discussed, uh, ideally throughout the course. Okay, so this is one of the paper, and then see this is another one. Say this is A72 processor and targeted in 16 nanometer FF plus, and it is kind of the frequency that they might have targeted was, yeah. Okay, so this is a kind of design structures, and the voltage that they targeted was typical zero point 0.8 volt and worst case 0.72 and all of that. And there are 500 plus scan chains in terms of DFT and 1 million cells, 1 million plus cells. So how did they achieve this, the whole thing? So basic floor plan, and then they are kind of adding certain, refining it, and then looking at a couple of things, and then all the densities, and then routing congestion issues, and then look at how the routing and the timing and all of that. So what and all they are actually trying to do it. So this whole thing, right, the whole course would be more on making you to a level where you would be best in the industry. Okay, see what is WNS, what is TNS, and how is your WNS is in, trending and all of that, and how can you look at your power, what is clock gating, and different timing analysis and different challenges with respect to clock gating, and useful skews and all of that. So you would actually go through each and everything. See here, optimize netlist hyphen area. So that is to what is the best way to area reduction. So someone was asking, right? So area reduction, and then say hyphen area in each and every step to, it's kind of 6% utilization improvements. Okay. And there is something called clock uncertainty, so decide what is the right values and all of that. Okay. So how did they kind of approach each and every stage? So what are the basic things? Say route of type and incremental, and considering crosstalk and power. So area recovery and all of that. So this is what I was just talking about. So each and every stage you need to know what is your target. Is it area is your target, or is it your performance is your target and all of that. Okay. So I would be just walking you through each and every papers. I would be sharing this all, which are more on the ARM based ARM course, which would actually give you seriously a good knowledge. So how do you highlight your the paths and ECO? So where are you putting the buffers? What is the meaning of on route buffering and all of that? So the goal would be 3 years down the line you should be able to write such papers. Okay. So that is how I actually look at. Uh, so this is something that I think someone from NVIDIA have presented it. Okay. And then Broadcom paper, this Broadcom. So this was my team. Okay. So we have presented a paper, and what and all we have done, each and every stage, what and all we have done. So signal EM routing, and then cell density aware routing, and everything. So here you look at shape, macro location, regions, pre-placement, routing pictures, and all of that. Your PG routing, what and all you look at, what kind of VR you choose, placement, okay, your HVT, SVT, LVT, what kind of PT mix, and then are you going to use single bit flops or multi bit flops, and what is your utilization at each and every stage, how are they kind of placed, so what layers you use for your clock tree cell, what kind of cell you use, NDR rules, useful skew, what kind of clock tree approach, and all of that. So you would actually learn each and everything. See, okay. So these papers are the my major goal. Whenever I wanted to give interviews, I actually go through these things for my refreshments. Okay. So you would also will share this thing, and you will go through all of that. Okay. So moving on to the practical side of it. So I would actually give few minutes break. Maybe I would say it's kind of bio break. You might want to go and take some water, and or use restrooms and come back. So just 5 minutes. So it is 8:16, and I prefer you coming back in 5 minutes. So we'll start shortly back at 8:22.